Okay, so today I want to continue the discussion of subgroup separability and residual finiteness. And my first task is to repeat the statement of a result I already mentioned last time. Of a note with Peter, Poplar, Colin Reed, Philip. And so that's the state, that's the following result. Let G be a finite degeneracy group, H in G a commensurated subgroup, and the notation H tilde I also introduced last week. So this is the profinite closure of H in G. So this is the intersection of all subgroups of G containing H and that have finite index in G. Okay, so that's the profinite, the closure of H in the group G equipped with the profinite topology.
What does commensurated mean?
And commensurated, yeah. So this means
every conjugate is virtually H.
yeah. So every G in G.
Okay.
If I intersect H with the conjugate to the G, I get something finite index in H. Okay. So the theorem says that the normal core of the profinite closure, which is the intersection of all conjugates of the profinite closure, is so which is a normal subgroup of G, of course. So this is a finite index in H. Okay, so I want to give you a proof. It's it's a statement that we first observed as a consequence of results on non-discrete, totally disconnected locally compact groups with so things that we had established with Nicolas Monod a couple of years ago, and yeah, together with these guys and especially Peter insisted a lot on us to find a direct elementary proof of this statement, not relying on results on non-discrete, totally disconnected local compact groups. And so that's the proof I want to present. Okay, so the first observation is the fact that H, being a commensurated subgroup, implies that also the profinite closure is commensurated. Why is this? Just because, so if you take an intersection of H tilde with a conjugate, so this is an intersection of two closed set in the profinite topology. So it's closed, and so it certainly contains the profinite closure of that. Okay, but now, if you look at so H, we know that H is covered by finitely many cosets of this, right? So the index of this is finite. Okay. But then a finite union of cosets of this will cover also H. Right? But the finite union of closed things is closed. So H is covered by finitely many cosets of this thing. But a finite union of closed things is closed. So H tilde is also covered by finitely many things. And so a fortiori, it's covered by finitely many cosets of a bigger.
Did you also just prove that H had finite index and H tilde?
No.
I thought you just proved, so that you got a finite index, you covered it with finitely many cosets of something that was finite index, I guess. So that sounds like you exhibited something. I guess that's what a subgroup is.
But this is much bigger than this, right?
Yeah, I guess. Right. Yes, I agree. Yes, sorry.
So H tilde is covered by finitely many cosets of. Okay, so far so good. Okay. But now, so what this means is that actually, so let me erase this. So actually, the theorem is it's enough to prove the theorem in the case where H is closed, right? So now from now on, we assume okay. So how do we proceed now? Okay, so let me introduce the following notation. For X, a subset of G, I will set H sub X to be the intersection of all conjugates of H under all elements of X. Okay? So the goal is to show that HG is of finite index in H. Okay. But now, the fact that H is commensurative, what does it mean? It means that if I take X finite, containing the identity, then Hx will be a finite intersection of conjugates of H, and so this will be of finite index in H. Okay. So this is true for any finite set H, and I impose that the identity is contained to make sure that I get a subgroup of H. And now the fact that H is its profinite closure, this implies that again, this will be an intersection of closed subgroups, so it's again closed. Okay. And so if I put the two together, it means that for every X finite containing 1, okay, I can find a subgroup W of finite index in G such that if I intersect W with H, I get Hx. So that's so Hx is closed, so it's an intersection of finite index subgroups of G, but it's a finite index in H. So actually, with one well-chosen finite index subgroup, if I intersect that with H, I must get the whole of H.
So you're choosing W to avoid the coset representatives of HX?
Absolutely. You just choose W to avoid all cosets representative of Hx in H, and that will do the job. Okay. And now I perform a usual trick. So a finite index subgroup contains a finite index normal subgroup. Okay. And now why can I say, well, if I look at Hx, it's contained, so now V is normal, so this is a subgroup, and it's also contained Hx, right? And this is contained in W, which is Hx. Okay, so what I get is that V Hx intersected with H is Hx. Okay, so for every finite set X containing the identity, I can find a finite index normal subgroup of G satisfying this equation. So what is my favorite finite subset of G containing the identity, a generating set? So I will apply this to a generating set containing the identity, and then I will show that for the given subgroup V satisfying this with a generating set, the same V will again satisfy this for the ball of radius 2 in my group, and then the ball of radius 3 in my group. And hence it will be satisfied by the whole group, and then so this will give me an upper bound on the, yeah. I mean, that's the strategy now, okay? So let me give you the details. So now we fix V.
V depends on X. Right?
Yeah, we fix.
You take the V corresponding to a generating set.
Yeah, well, let's fix the V satisfying star for X, a generating set. So we fix that, and now let's study the collection Y of V of all sets, finite sets Y containing the identity, which satisfy the same equation for V. Now the point is that the set of such y's is stable, has good properties. So claim 1 y1, y2 are in yv and the union is also. Okay, so this is playing with unions in intersection. So you have to look at this. So this is certainly contain that. Okay. But this is V times. Okay, so this is an intersection of conjugates under element where elements run over this union. So this is the intersection. That's an equality actually. And then this is at most this. And now I use the assumption to get that this is which is okay. So that's claim 1, and now we have claim 2. The fact that if y and 1t belongs to this, then this belongs to y. Okay. So this is a similar computation. So I will repeat that. Okay. And now what's going on? So now I can finish because so X, my generating set, was in there. I want to claim that Xn is there for all n, which follows from the two claims. My claim 1 and 2. Okay, and so what does this give to me? So if I look at the intersection of H with V, so this is contained in this which is equal to that for all n. Okay. So H, the intersection of H with V is contained in HG. Okay. But this, the index of that here is finite because V is a finite index in G. So this index must be finite. Okay, so yeah, so it's a lot of unions and intersections at the end of the day. You get this bound on the finite index of the normal core. Okay,
It will also give the more sophisticated proof.
yeah. The other proof, which is probably, well, so, but this would only happen when you.
You can, I think just try the backboard, just moving it up a bit.
Okay. So yeah, the alternative argument relies on a proposition that I observed with Mono. It says the following: let G be compactly generated totally disconnected locally compact group. If the intersection of all open normal subgroups of G is trivial, so this is saying that G is residually discrete. Every element of G which is non-trivial remains non-trivial in some discrete portion of G. That's the, so if G is residually discrete, then G has a basis of identity neighborhoods consisting of compact open normal subgroups.
So this is kind of obvious in the case of profinite completion.
Exactly. So if G is a profinite group, which is a very good example of a compactly generated TDLC group, then yeah, G is residually discrete, it's even residually finite, and yeah, you know very well that in a profinite group, you have a basis of identity neighborhood. But the point is that this result need not the group to be compact to start with. It's only, you only need compact generation. Okay?
But you're now going to use it not just in the case of a profinite completion.
Yeah. So then, exactly, you really need to exploit the potential non-compactness of G. So now in the situation of the result, so you have H in G commensurated. Okay. So now if you want, you pass to H, the closure of H in the profinite completion of G. So this is now I'm not looking now at the profinite topology on G. I really complete. So I am in a profinite group, and I look at a closed subgroup here. So this I cannot claim a priori that this is commensurated by the closure. But the same argument as before shows that at least the closure of H is commensurated by G. Okay. And now what I do is to define, if you want J, the abstract group generated by H bar and G. And G is a finitely generated group. So this is a group J. No, well, it would be, it's related to the Schlichting completion of yeah. This group is closely related to the Schlichting. You have a map between the two, but anyway, yeah. So this is an abstract group, an abstract subgroup of the profinite completion. It's generated by a compact group and a finite set, and it commensurates a profinite subgroup. So for such groups, you always have an intrinsic TDLC group topology, which makes this one an open subgroup. So this is, in a unique way, a TDLC group, uniquely, such that the inclusion is continuous and open. Okay? But now, this group leaves, so the embedding, okay? This is a continuous embedding to check that homomorphism of topological group is continuous. It's enough to check that it's continuous at the identity. But at the identity, close to the identity, I'm just looking at the embedding of H bar in G hat, which is a closed subgroup. So this is certainly continuous. And this is a profinite group. So that's residually finite. So this one must be residually finite too. So I can apply the proposition. And the proposition says every identity neighborhood, for example, H bar, J, contains a normal identity neighborhood. Okay? So H tilde, H bar is an identity neighborhood in J. So it contains a compact open normal subgroup of J. Okay, but an open subgroup of H bar is a finite index subgroup because this is a compact group. And so you have produced a finite index subgroup of H bar, which is normal in J. But J is dense in this one, right? J, so this, the normals, it will be normalized by G in particular. So now you pull back everything in G, in the original group G, and you're done. Anyway, hyperplane. Yeah. But the point is that, yes, this is...
Extraordinary argument. It's very, very strange. I mean, it's great.
I mean, these kind of things, yeah. Yeah, we are, yeah.
Well, I mean,
You know, it's...
you did not completely avoid the topological language either in the first place. Just for
It's
convenience.
hidden. What do
No,
you
it's
see?
not hidden. I mean, you used clone.
You use the profinite topology. Yeah, you use topological groups there.
So something very elementary
Yeah.
about it.
Anyway, so
But normally when you take an argument, normally when you take a slightly complicated argument about a separable subgroup and you translate it into the profinite completion, you get a very clean and quick proof of it. Whereas here you then need to go via your beautiful result about algebra. Totally disconnected from everything. Which is what I find very extraordinary.
okay, so now let's accept the theorem and let's proceed from there. So one consequence is a criterion that I've already mentioned before. So back to the consideration of lattices in products of trees. So this is a discrete group acting co-compactly on the two trees, and the trees are leafless. I impose this just to make sure that the action is minimal on both sides. And, yeah. I want trees with more than two ends. Okay, then the following are equivalent. So the first assertion is that gamma is reducible. And I want to be, again, remind you the very precise definition of reducibility we have here, more precisely. Gamma is virtually, so let me take a shortcut here. Gamma 1 cross gamma 2 is a finite index in gamma, where, so gamma will be virtually a product, and the two factors in this product are the two kernels of the projection. Okay, so if I want to be correct, I think I have to write that gamma I is a projection on both the of the kernel of the action of gamma on the other. This was carefully prepared. Yes. Okay, so it's easier to say it in words than. So that's the first assertion. Gamma is virtually a product of lattices in the individual factor. The second assertion is that the projection on the first factor of gamma is discrete. Third assertion is that for all vertices in the first tree, the stabilizer of that vertex is separable in gamma. And fourth, there exists a vertex such as gamma B.
To be clear, in 2, 3, and 4, all the subscripts are 1 and not i's. Is that
Yeah,
what
it's
you-
asymmetric.
You only need to
Yeah.
look at one factor.
Yeah. Yeah, absolutely. So the equivalence between 1 and 2, well, yes, 1 implies 2 is clear. I think that's clear enough, right? And 2 implies 1 that was already observed by Martin Schachar. And the point is that you use the general factor lattice for it. So for any lattice gamma in G locally compact, and for every n closed normal subgroup of G. So if a lattice maps under a quotient map of G to a lattice, this is equivalent to saying that the intersection of the lattice with the normal subgroup is a lattice in the normal subgroup. So then gamma n mod n is a lattice in G mod n if and only if gamma intersecting with n is a lattice in n. Okay? And now this is exactly relevant to our situation. We are assuming that the projection of gamma to the first factor is discrete, but then it must be a lattice. And so you will get a lattice in the other factor by this principle. Okay. So what else? So 1 implies 3. I think that's clear enough too. But because we are dealing with a product of free groups virtually, and then these are finite subgroups in that case. So we are just saying that finite subgroups are separable in a group which is virtually a product of free groups. So 3 implies 4, again, that's clear enough. and 4 implies 2. So that's what remains to be shown, and that's a consequence of the theorem. So let me explain this. So we assume that gamma V, that we call H, is separable in G, which we call gamma. But gamma is finitely generated, it acts co-compact in a product of trees. And H is commensurated, as we observed last time. So we are in the situation of the theorem. So by the theorem, the normal core is a finite index in H. Okay? But this now, what is this guy? It's a normal subgroup which fixes vertices. It fixes an orbit of vertices on the first tree, right? So this, it must act trivially on T1. Okay? So the stabilizer of a vertex has a finite index subgroup which acts trivially on that tree. So this means that the projection of gamma on the automorphism group of the first factor has discrete image. So the image, the projection of gamma on the first factor has discrete image. Okay. The projection means I mod out this normal subgroup and then I get a group acting on a tree with finite vertex stabilizers. So this is a discrete. So okay, and so and so these equivalences are useful in both directions in a sense. So for example, if you remember what I mentioned about the example provided by Danny Wise in his thesis, it was a BMW group of order 3-2, and he proved by hand that the vertex stabilizer was inseparable. So actually, so this means that his lattice is irreducible. And what I want to show you is conversely the inseparable. If you have another means to show that a given example is irreducible, then it will be very useful to know that the vertex stabilizers are inseparable. And to do that, so I still go through more definitions. So abstract group theoretic definition.
So Wise also has a proof of something like 4 implies 2, right? Which goes
Wise as a proof. So there is something hidden in the Heilbrunn-Weiss first paper.
No, I think it's in one of his own papers. I don't remember if it's the figure 8 not paper or the complete square complex paper.
I'm sure that he was aware of this.
He has a virtually horizontally clean implies virtually clean statement, which I think is almost exactly the same from very similar.
Yeah.
I mean, particularly you can prove if a VH complex is virtually horizontally clean, then it's virtually clean. I think that's more or less 4 implies 2.
Yeah.
4 plus 1.
Yeah. You're right. I'm sure that certainly he's aware of this.
Oh, sure.
You can probably get it.
I'll see it.
Okay, definition. So if H is a subgroup of a group G, you define QC GH, the quasi-centralizer of H in G, to be, by definition, a collection of elements of G such that G centralizes a finite index subgroup of H. Okay, so in other words, if I look at the centralizer of G in H, I want that this has finite index in H. Okay? And you convince yourself that this is a group. And moreover, if you centralize a finite index subgroup of H, then in particular you normalize a finite index subgroup of H, and so if you must commensurate H. So this is actually always a subgroup of the commensurator in G of H. And it's not only a subgroup, it's a normal subgroup. I should use colors. So that's okay. So this is the quasification of the centralizer. The centralizer is a normal subgroup of the normalizer, and the quasi-centralizer is a normal subgroup of the commensurator. So this is all straightforward. You need to get used to that. And now, so what do I speak about this? It's another corollary of the statement, the theory. So let G be finitely related such that every infinite normal subgroup of G has trivial centralizer. Okay, so I don't want G to be virtually a product, for example. Okay. This is some kind of algebraic irreducibility assumption on G. G can be a simple group, for example, but it can be. It applies to a lot more groups. If G is reasonably finite, then for every commensurate infinite commensurating H in G, the quasi-centralizer of H in G. Okay? So I make this assumption on usual normal subgroups, and then under the assumption of residual finiteness of G, I get the corresponding quasi, well, almost normal version. Okay. And the proof is the following. So let X an element of the quasi-centralizer. Okay, then. So there is a finite index subgroup H which commutes with X. That's the definition of quasi-centralizing H. And now I do what I already did before. The residual finiteness of G says that the profinite topology is Hausdorff. But then if you commute with something in a Hausdorff topological group, you also commute with the closure. Okay. But then I will commute with any finite index subgroup of that. And here for n, I take the normal course. Okay. And now if I assume that H was infinite, this is still infinite, and by the theorem, n is a finite index. Okay? So the theorem implies that n is still infinite. Okay? But then I commute with an infinite normal subgroup, and then by assumption. Okay? So I
really need that the identity is closed.
Absolutely. In this proof.
Yes.
And the point is that, so not only it's needed by the proof, but it's needed by reality. because you can turn this fact into a criterion of residual finiteness. And I want to illustrate this with examples that we all know and cherish. So, corollary, we recover a well-known result of Meskin from the 70s, which is the fact that G, the Bohm-Slack solitary group, is residually finite if and only if m is 1 in absolute value, or n is 1, or absolute value of n is the absolute value of n.
That's not due to solitaire?
No. So, yeah. So Bohm-Slack and solitaire consider these groups for the Hopfian property. I mean, they have a characterization of when these groups are.
Oh, so they were able to show when they're non-residually finite?
In some cases, but the point is that some of these groups are non-residually finite but still Hopfian. So it's not the same conditions that you get.
Which one? What's an example of one that's non-residually Hopfian?
I don't remember the condition for being non-Hopfian is stronger. Anyway, but now let me connect this with the previous one. So this is an H&N extension. So it acts on a tree. Okay, G acts on T, so that's a tree. Okay. And now, so I will only show this direction. The other direction, well, it's not a consequence of that. So you need to use other results. So let's argue about this direction. So we will argue by contradiction and assume that these conditions are not satisfied. I claim that, so if m is not 1 in the absolute value, n is not 1, and m and n differ in absolute value, this has a precise geometric meaning for this action. The fact that m is not 1 and n is not 1, this implies that the G action on the set of ends of the tree has no fixed point. Okay? Think about it. So if you so this is a vertex transitive action, right? Now this means, what does it mean? It means that a vertex stabilizer, it has no orbit of size 1 in its neighbor. So there cannot be a global fixed point at infinity, because already a vertex stabilizer does not fix at infinity. Okay? So that's clear. And now the condition, the other condition really means that the G action on T is faithful. So this is something else you need to check. But okay. And now, so you get a group acting vertex transitively without a fixed point at infinity on a tree.
It's equivalent. These are equivalent.
Yeah, it's actually equivalent. Yeah, absolutely. And so from this, I conclude that for every normal subgroup of G, which is non-trivial, the centralizer of M is trivial. Okay, so that's an argument. In this case, it's due to this, I think, but it's the usual. So a normal subgroup of a group acting on a tree with these properties, we still act without proper invariance of a tree and without fixed end. But then the centralizer of this will consist of elements with constant translation length, so it must be the identity. Okay. So you're exactly in the situation of the proposition of the previous corollary. And now H, the cyclic group generated by A, this is commensurated again by the presentation. But now H is abelian, so H is contained in its own quasi-centralizer. And so D is not very different. Of course, so Meskin proved it directly, but if you look at Meskin's proof, he discusses the GCD of M and N, and so there are, he directly find arguments saying that this relation cannot be satisfied in finite groups. But, so at least it shows that the corollary can be useful to check that some groups are not really finite. And let me, still build up on this. So let G be finitely generating as in previous corollary. So every normal subgroup which is infinite has trivial centralizer. And H in G be infinite and commensurated. If G is readily finite, then for every normal subgroup of G, non-trivial, the intersection of H with N is infinite. Okay, so again, you know that in every group, if two normal subgroups have trivial intersection, they commute. Okay? What I'm claiming here is that if I have one normal subgroup and one commensurated subgroup, and I assume that they have finite intersection, then they quasi-commute. That's the point. If the group is really finite. But if they quasi-commute, because again, by the previous result, the quasi-centralizer was trivial, so you get a contradiction. That's essentially the proof of this, how you deduce this corollary from the previous one. And now, the last thing I want to say for today is that this in turn has is a meaningful statement for lattices in products of trees. So now we come back to a result of Mark and Shahar that they used as a criterion of non-residual finiteness for lattices in products of trees. So let gamma input T1 or T2 be discrete group acting co-compactly. If gamma is irreducible and residually finite, then the kernel of the projection of gamma towards T1 is trivial. Okay, and this follows, so Mark and Shah proved this with a slightly with a slight additional assumption on the action, yeah. But this statement follows from what I explained. And how does it follow? So the point is that this kernel N, so this is a normal subgroup of gamma. Okay, and now I can take H, the stabilizer of a vertex in the second factor. Okay, so this one, it acts trivially on the first factor, so its action on the second factor is proper. But then if I look at the intersection, which is the stabilizer in N of a vertex of the second tree, this is finite. Okay? But again, H is a commensurated subgroup. So I have a normal subgroup whose intersection with a commensurated subgroup is finite. So I can deduce that N was trivial provided H is infinite. And saying that H is infinite is exactly saying that gamma is irreducible. So finally, yeah. It's still alive.
You didn't break it anyway.
Next time they will be confiscated. Okay, so yeah, just now as a as an a kind of introduction for next week. So remember, we had this group gamma 1, these two groups gamma 1 and gamma 2. Now I come back to gamma 2, which are the 4 generated groups. Okay, so this was an example of a BMW group, so acting on the product of two 4 regular trees. And I promised you to show that this is not reasonably finite. Okay. So what you can observe if you play with this presentation is that if you conjugate x cubed by a, you get y minus 3. And you do the same with b, you get the same answer, you do the same with a inverse, and b inverse, you get the same answer. Okay. So this means that actually both of these elements, they commute with an index 2 subgroup of AB. Okay. But AB, they act vertex transitively on the vertical tree. Okay? So if I project these two elements, they commute with a group acting with 2 orbits of vertices on the vertical tree, so they have to act trivially. On the vertical tree. Okay, so the projection to the first factor is non-trivial, as a non-trivial kernel. And so gamma 2 is non-reasonably finite, provided I show you that it's irreducible. Okay, so this is the so this will be the subject for my talk next Thursday. I will finally explain how Mark and Shahar checked that certain lattices are irreducible, and this will apply to gamma 2. And I will also mention how, I mean, here it looks a bit specific to this example, but actually from the discussion before, you can also turn this into an algorithmic criterion, checking that some B and W groups are not reasonably finite, so this I will mention. And yeah. And in the very last talk, probably, I will come back to simple locally compact groups and discuss something else. That's all for today.
Yeah, in this proposition over there, do you get some information on the intersection of finite index of gamma out of the proof?
Absolutely.
Yeah.
Yes. You can carefully go through the proof, and yeah, the proof gives you elements that are in the finite residual. And you can apply this to gamma 2, and so actually, I think it's something like the commutator. I should double check, but it's something like the commutator of x to the 6 with y to the 6 is in the intersection of all finite in the finite residual.
Do you have such examples which satisfy your proposition but which are not arithmetic? Reducible, residually finite but not arithmetic. They must exist, but maybe for higher valencies, because for
Yeah, I certainly have no example that are irreducible, reasonably finite, and just infinite, but that are not arithmetic.
yeah. So I was checking like with a computer for small like product of trees of valency 4, valency 6. I didn't find one orbit, but it's maybe just very small valence. Right?
Yeah, but yeah.
Clearly, you remarked it as well, right?